So this is the next equation, and we will define the equation or we will derive the equation for an electrical potential or potential difference between 2 points A and B in an electrical field. Again, this is considering electrostatics. So, and next what we will do is we will find out what is known as or define the Maxwell's second equation of electrostatics. So the Maxwell's second equation says that del cross E is equal to 0, which is that if you are taking a line integral, or if you are moving an electric field, and if you are starting from a point and if you are coming back to the same point, then the net work done will be equal to 0. That is, the electrical field is a or electrostatics field are conservative field. So to define that, that is implied by the Maxwell's second equation, which will be derived. So if you are having an electric field distribution, which you can depict by the arrows, so this is the electric field E, and if you are moving from a point A to B in this electric field, and you are considering that you are taking the reference with respect to origin, and this is your RA position vector, this is your RB position vector, and this is an infinitely small dl area which you are considering, and this is a R vector. So this is a dl area which is your motion. So to derive, you are considering that you are moving against the electrical field. So this is the electrical field, and you are moving from point to A to B. You are moving a charge Q from A, and your final destination is B, and this is done against the electric field, such that this could be a negative charge or this could be a positive charge, and the field itself could be positive, and you are moving from A to B. So it's evident that when you are moving from A to B, some amount of work needs to be done. You need to do work. So, and also you will need to provide some kind of force. So the electric field intensity can be given by Q divided by or F divided by Q. So the electric field intensity on the charge Q which you are trying to move can be given by F divided by Q, and based on the equation for the electric field intensity in Newton per Coulomb, and based on this you can write that F equal to QE, considering the field is E in this case, and the work which you are doing can be written as, based on the Newton's law, it can be written as minus F dot dl. The minus sign implies that you are trying to move a positive charge in a field which is positive, and this movement is done against the electrical field. So if you are substituting the value of the Q, this is the first equation which you are derived, and this is the second equation which you are derived. If you are substituting the first in the second, what you will get is d by dw is equal to minus QE into dl. And the whole idea what is that you will have to do an integration here in such a case that you are moving from A to B, and you are moving the charge such that it is E dot dl. So you are doing a line integration to find out the total path. So the work can be written as it is minus Q A to B E dl. Now the potential is equal to the work divided by charge. So it becomes, when you are using this equation for the potential difference between A and B is equal to work divided by charge, what you will get is that this Q will cancel and you will get A to B E dot dl. And if you are taking a simple case of a charge distribution due to a point charge, or the field is due to a point charge, then you can give the equation of E as Q upon 4 pi epsilon naught r square in the direction of AR. So if you are saying that this is due to a point charge which is located here, and if the point which you are trying to find the electric field is here, and this is a R, so this is the equation of the electric field. Now if you are saying this is my fourth equation, this was my third equation which I got, so you can substitute this here, and what you will find is VAB is equal to minus A2B Q upon 4 pi epsilon naught R square AR. And to integrate it, you will have to add something known as AR dr. So when you are integrating it, it will be something like 4 pi epsilon naught into 1 upon RB minus 1 upon RA. So if you are assuming that the point you are starting from infinity, my starting point is infinity, then this will become 0. And if you are considering this as my R, if you started from infinity and you came into this field, and now you are at R position, so this full equation, if I will write here, this is my fifth equation, and this full fifth equation will become something like my electric field between A B, which can be generalized as V, and it can be written as Q upon 4 pi epsilon naught R. So this RB will become, RA will become equal to 0, and my RB will equal to R, which is this R, or which I can generalize at. So this is the equation of the electric potential specific to static electricity. So the same can be also considered, or the same can be applied when you are considering the electricity in motion or considering the current.